So we finished balancing chemical equation, and I think there's a question on OWL about this. And the OWL, you have until Thursday to do that because as I promised 1 week after. And then we started chapter 3. Now, if we're going to summarize chapter 3, it's how we look at the mole concept and how it's related to the mass of an object and the number of particles. So if we're going to remember the triumvirate, from moles going to the mass, all you need is you multiply it with the molar mass. And the molar mass is just your formula mass or your molecular mass, just expressed in grams per mole. And if you're given the mass, you want to go to moles or you want to convert it to moles, all you need is you divide it with the given molar mass. And if you have the number of moles, you want to go to the number of particles, all you need to do is you multiply it with AN, which is your Avogadro's number. And if you have the number of particles, you want to determine the number of mass, you're going to divide it with the Avogadro's number. So that's the name of the game of the first part of the chapter. And then we end up with determining the so-called percent composition, wherein we just look at the contribution of each element in a given compound. So pretty straightforward math. Okay, so I want you to go over the lecture that we have. When you practice, I would suggest you start your practice by this time. Okay, so we're going to continue today with the concept of empirical formula. Okay, so when we're talking about empirical formula, as shown here, they said that's the simplest formula. Okay, that's the formula of a substance written with the smallest integer subscript. So this is the smallest whole number ratio of a given formula. So for instance, if the formula given is N2O4, you could say if you divide both of the nitrogen and oxygen with 2, you get a ratio of 1N for every 2 oxygen. If you have an empirical formula for hydrogen peroxide as H2O2, if you're going to look at the ratio of that, you divide both of them by 2, you have HO. So all of them are empirical formula, the simplest whole number ratio. Okay? Now, why do we need to know this empirical formula? Because this concept of empirical formula, they use this to determine, okay, the given formula of chemicals. So by having the empirical formula, they know the simplest whole number ratio of each element that is in the given chemical or given compound. And the way that they look at it is using the empirical formula, they will be able to get this molecular formula, which we're going to talk about later on. Okay, so the way that they look at the empirical formula, so whenever you do a percentage composition and you know the empirical formula, all you need to do is convert anything. Okay, you can assume 100 grams, and then what you're going to do is convert that 100% to 100 grams. So whatever the percentage that you have there, you just convert everything to grams. And once you convert it to grams, you're going to convert this to mole. Okay, so from grams, you're going to convert it to moles. So how are you going to convert each of the elements from grams to moles? You divide it with the respective atomic mass or molecular mass, but in this case, since you only have one atom, so you don't really have a molecule. So your molar mass there, not really a molecular, your molar mass there is just the atomic mass of each element. And then you're going to get whole number ratio. So you're going to manipulate it such a way, usually what they do, you divide all whole number ratio with the lowest ratio, because the lowest ratio will give you 1. Okay? So if the result is still not a whole number, you're going to multiply it by a factor to make it whole number. So if the decimal portion is 0.5, you can multiply by 2. If it's 0.33 or 0.67, you multiply by 3. If it's 0.25 or 0.75, you multiply by 4. So you don't round it up. But we have an example on that. Okay? So if you're going to do this concept here, so maybe we can start with what we have left last time. So in our previous problem, okay, when we determine a hydrocarbon, we end up that we have a 92.3% carbon and a 7.7% hydrogen. Now the one being asked now is, what is the empirical formula? Okay, so if you're going to look at this, you can always what? From 92.3% and 7.7%, you always convert these to, anyone?
Grams.
Grams. And then once you have it into a grams, the next thing that you're going to do is to convert it into the respective mole. So how are we going to do it, convert to respective mole? We divide them by the respective
atomic mass.
Atomic mass or molar mass, but in each atom or element. So we could say this is what? 12.01 grams per mole. And this would be 1.01, or you could say 8 grams per mole. So if you're going to look at the units, you canceling out the grams, giving you the number of moles. Okay, so from that, what do you get here? 92.3 grams divided by 12.01. Anyone?
7.69.
Okay, or if you can put everything first, 7.685. And this one would be around 7.7 divided 1.008. So this is around
7.638.
Like that?
Yeah.
Now, if you're going to divide both of them, so this is not grams, this is mole. So if you're going to divide both of them with the lowest one, so this will give you around 1, right? Because you have here, what's the number that come out in the carbon? Is 1.006 something. So if that is the number, you can always round it up to 1. The one that you cannot round up is like 1.25, 1.33, but this is 1.006, so this is 1. So if you're going to answer the question there, so all you need to do is write this thing here. So the empirical formula is C1H1. And they are in the simplest whole number ratio. You cannot simplify them further. So that means this is your empirical formula. So you see here, we started with what? Percentage composition. And we end up with the empirical formula. So everybody got that?
Yes.
Yep.
Okay. Now, we discussed empirical formula. Now, how is it different from molecular formula? So when we're talking about molecular formula, this is a formula for a molecule in which the subscripts are full number multiples of the subscripts in the empirical formula. So when we're talking about molecular formula, that's the exact number of elements in a given compound. That's the exact number of atom in a given molecule. And usually, as they said here, it is a multiple of empirical formula, a whole number multiple. So usually, okay, you are asked to determine the molecular formula aside from the empirical formula. But you can only do that if you're given the molecular weight. So to determine the molecular formula, the first thing that you do is you compute the empirical formula weight. And then you're going to find the ratio of the molecular weight that is usually given to the empirical formula weight. And then whatever, okay, the number that you got, you multiply each subscript of the empirical formula by n. So we're going to use that in the problem that we have. So remember the benzene? So we end up with this as the empirical formula. So it says there that its molecular weight is 78.1 AMU. So you are asked now, what is the molecular formula? So what do? We need to get, what's the empirical formula weight for this? So you have what? 12.1 plus 1.008, so around 13 point. Is that like this? Or around 13.02? Right?
Yes.
So all we need to do now is we determine the n. So we have 78.1 divided by 13.02. So what do we get? What do you get?
6.0.
Okay. 6.0. So what do we do now? So this one, we're going to multiply that by 6. So this becomes C6H6. Now the question, is there a way for us to check if this is correct? Anyone?
You go it back to the empirical formula.
Is it going back to empirical formula? Is there a way for us to check if this is correct? The answer is yes. What do? We get its molecular weight and see if it's really 78.1. So if we have that, 6, so you have here 12.01 times 1.008. So what do you have there? 6 times 12.
72.06.
Okay, 72.06. And this is around 1.008 times 6, so 6.048. So when you add them, okay, it will give you around 78.1. So that's the way for you to check if you got the correct molecular formula. Analyze. We have another more examples, so don't worry. So what we do now is we're going to get the empirical formula given the percentage composition, and with some problem that has this so-called molecular formula. Okay, so let's proceed to the next question. So you have your sodium pyrophosphate used in detergent preparations, composed of 34.5% sodium, 23.3% phosphorus, and 42.1% oxygen. So what is its empirical formula? So what's the first step that we have?
Convert to grams.
Convert to grams. So you can put here 34.5 grams of Na, 23.3 grams of phosphorus, and 42.1 grams of oxygen. And then once you convert the percentage to grams, you're going to convert them to moles. So in doing that, you're going to divide them with the respective atomic mass. So what's the atomic mass of sodium? Anyone?
22.99.
22.99, so grams per mole. And then the phosphorus?
30.97.
30.97 grams per mole. And oxygen would be?
15.9.
15.99. So if you're going to look at this, yes, question?
Yeah, for these, is it okay if we do round up, or does it always have to have the decimal point?
Yeah, I mean, you're going to see it is when you look at the ratio of the mole. So if it's just around small numbers, it doesn't really be a big deal.
Okay.
The big deal is you round up, let's say a 0.25. That's really going to be an error. But here it's fine.
Okay, thank you.
So the initial number of moles that you're going to get here, so 34.5 divided by 22.99. What do you have here?
1.50.
Okay, 1.50, and then 23.3 divided by 30.97. This is what? 0.7. 7 what?
5.
52.
Okay, so 7.5 or 7.52. You can what we call has more than that one that you have here, because this is not the final answer yet. Okay, you're going to divide them yet with the lowest number of moles. So for oxygen, how much do you get?
2.633.
2.633. So you have this fraction ratio. Now you want the ratio to be whole number. So the next step that you're going to do is you're going to divide it. The rule that you have is with the lowest mole. So in this case, you can use this one. So what do you get if you're going to have this ratio? If you're going to divide it with this number, so this is around what? 2, right?
That's
Is
one.
this around 2?
Yes.
Yes.
And then this is around 1, and this is around?
I put 3.5.
Okay. So you cannot round up 3.5. So what you have here is one of them is a fraction. So this is still not your empirical formula, because the definition of our empirical formula is the simplest whole number ratio. So how are we going to make this into a whole number? Anyone? It was given in the
Can
previous
you
slide.
double it?
Multiply by
Yep. You multiply everything by 2. So if you multiply that one by 2, make sure you multiply everything by 2. So you end up with
4, 2, 7.
So that is the empirical formula. Now you ask yourself, can that be the simplest whole number ratio? I think yes, because 7, you cannot simplify 7 into a small number. Analyze. Question before we go to another example? You can always go to our recorded video if you want to understand it at your own pace. Okay? So let's go to another one. So in this case, it's not only the empirical formula. So we have hexamethylene. It's one material used to produce nylon. So it is composed of 62.1% carbon, 13.8% hydrogen, and 24.1% nitrogen. Its molecular weight is 116 atomic mass unit. So what is its molecular formula? So you have an additional question here. But the step that you're going to do is just similar to what we did in the previous problem.
So we find the empirical first and then the molecular?
Yeah.
Okay.
So the first step that you're going to do is convert everything to grams. And then you're going to divide them with the respective atomic mass. So carbon is still 12.01. Hydrogen is 1.008 grams per mole.
Is it okay if we still do dimension analysis?
I don't think you need a dimensional. Yeah, I mean, you always do that thing here. But as you could see here, it's the mole that you need to get. So grams per mole, okay? So what you do here, grams divided by grams, you have the moles. Grams divided by grams. You have that's a 1/1 per mole. So that would be the mole, okay? And then here you have, what's the molar mass of nitrogen? 14.01. Because that one is similar to this. I just don't want to use it this way because it's just has too much what? Space. But they're just the same. Okay? I want you to convince yourself that this one is the same as that one. I just don't have space, that's why I didn't do it. But that operation is just the same as this one. And if you have any question of that, then I would suggest you practice your math. Okay? I cannot explain that to you at this time, but this one is just the same as that one because 62.1 times 1 is equal to what? 62.1. So you just divide them with 12.01. Okay? So what do you get here?
5
How many moles?
5.171.
171. Hydrogen would be
13.690.
okay, 69. And nitrogen would be
1.7.
so what number are we going to divide each one of them? with,
1.72.
1.72.
okay, because that's the lowest one. So you end up with what number here?
3,
This one,
8,
and this is
1.
1. So you end up with the formula that's C3H8N.
Wait, sorry. Where did you get the 1.72 from?
That's the smallest mole fraction. So what do we do is we need to make them into a whole number. So the way that we're going to do is we divide it with whatever the lowest mole among the available element. Question?
Mm-mm.
So everyone convinced that this is the empirical formula?
Yeah.
Yes. And now we
Because
have
the next thing that we're going to do is we're going to determine the molecular formula, and we're given here the molecular weight. So what we need to do is we need to determine what's the empirical formula weight for this. So that is what? CHN. So that's 12.01, 1.008, and 14.01. So if you're going to get here, what's the number that we have? 36.03. This one is 8.064. And this one is 14.01. So this is equals to what?
that's the AMU.
Yep.
$58.104.
Okay, so 58.104. So what we're going to do now is we have the molecular weight divided with the empirical formula weight. So you have 116 divided by 58.104. So that will give you equals to what? I think 58 plus 58 is 116, so it's around 2. So what you're going to do, you multiply it with the subscript here. So you end up with C6, 816, and 2. So this is your
Molecular formula.
molecular formula. Question?
Not right now.
No.
So I'm not sure, but usually there's a question like this in the exam.
Actually, I do have a question. Why does the two never mind. Never mind. I thought the two only added to the end, but it added to everything.
It's everyone.
Yeah.
Okay. So the next thing that we're going to do is we're going to expand the concept that we have about the mole. Okay. So what we have discussed so far in this part is just in one species, in one compound. Now what if we have a reaction? Okay. What if we have a reaction that is represented by chemical equation? We can expand the mole concept to that. So we now have here this so-called stoichiometry, the calculation of the quantities of reactants and products involved in a chemical reaction. So what we have here, the coefficients of the balanced chemical equation may be interpreted in two ways. Okay? So whenever we have a chemical reaction or represented by chemical equation, there's two ways to represent it. It can represent the number of molecules that are reacting with one another, or it could also be the number of moles that are reacting. So the stoichiometry coefficients that we have there, you can do it in terms of molecular level or molar level, but you don't intermix it. So for instance, if you have like this one, this reaction, so if we're going to represent this reaction, so I can put this like this and like this. So there's two interpretations that I have here. I can interpret here for two molecules of hydrogen reacting with one molecule of oxygen, you produce two molecules of water. So that's the molecular level. Now I can also make it in terms of mole level. For every 2 moles of hydrogen that react with 1 mole of oxygen, you produce 2 moles of water. Now what you cannot do is, for every 2 moles of hydrogen reacting with 1 mole of oxygen, you produce 2 molecules of water. You cannot do that. So you either stick to molecules level, molecular level, or moles level. Now the moles level, that's the one that we have in terms of stoichiometry. Okay? So the way that they look at it is to find the amount of B, whether it's a reactant or a product, given the amount of A, another reactant or the product, these are the steps that you're going to do. Or I'll put you back to what we have learned earlier.
I kind of like the way you did it earlier.
Okay, so remember this. So that's the reason why I cannot make this into a triangle, because I can make this as mass A, mole A, particle A. And what do? I make here mole B. And then the same thing. Okay, so I have here B particle. And then I have here the mass of B. So you do the same thing as this one. So the question now is, how am I going to combine them? Where is the connection? Where will I put the arrow to combine these two? So this is substance A and this is substance B. So in stoichiometry, we can combine them. Now, where do you think I'm going to put the arrow? That's the arrow that connects them. And how will I know how much of mole A will produce mole B? I have the balanced chemical equation. So when we do the what we call the dimensional analysis, we're just going to extend what we have. So maybe we start here and we need to go here. So you start with what? Mass A, and then the molar mass, or you divide it with the molar mass. So for every 1 mole of A, you have a certain gram of A, and then that's already here. So for every whatever the stoichiometric coefficients that they have with A, there's a corresponding coefficient of B. And then whatever the mass of B, oh, not that. For every, let's say 1 mole of B, there's a corresponding mass of B. So you just extend the calculation. But the concept that you need to remember is mole is the one, okay, the central concept to connect the mass and the number of particles. Now, mole also, that is the concept that you're going to connect your given substance with the other substance that is reacting or being produced by it. That's why somebody put in the chat a triangle. No, you cannot make this a triangle. Okay, because these two will not meet. A triangle is like that. But as you could see, okay, these two don't meet. They have to pass through the mole. That's why I cannot make this into a triangle. The way I do is a triumvirate, but they're not really what we call particles and mass won't unite. It's just most of the mole. So if we're going to go back in this slide, so it's just the same as what I did. So you have here the mass of A. So you need to go to the mole of A, convert it first to the mole of A, and then convert it to the mole of B, and then convert it to the mass of B. So it is this concept that is most important. Okay? So let's try. So we have here propane, which is normally a gas, but it sold as fuel compressed into liquid in steel cylinder. So the gas burns according to the equation. So 1 mole of propane reacting with 5 mole of oxygen to produce 3 moles of carbon dioxide produced, and also 4 moles of water. So how many grams of CO2 are produced when 20 grams of propane is burned? So what is given? What is given here?
20 grams.
Okay, so the one that's given is the 20 grams. And the one that we're being asked is how many grams of this? So if you have 20 grams of this one, how many grams of this will be produced? So maybe we start with 20. And what's next? We need to convert these to
Moles.
moles. So we need to divide it. So for every 1 mole of C3H8, there is a corresponding mass, which is just the molar mass of this one. So I could put it around what, 44 something? Now once it is now in moles, what's the next thing that I'm going to do? I need to get the mole ratio of this and this one. So how I'm going to put the moles here? Which is the numerator and which is the denominator? Anyone?
Mole A is in the denominator and mole B is in the numerator.
Okay, so what will I put here?
You put C there and H on the bottom?
You cannot have a C and an H.
No, not.
Okay, so you put the CO2 here and you have the C3H8 here.
Okay.
Analyze. Why did I place it like that?
Because you want to get rid of it, the C3H8.
Okay, you want to get rid of the C3H8 and convert it to CO2. Now, what are the numbers that I'm going to put in front of the moles? Anyone?
1 for the C3HO, C3H8, and then 3 for CO2.
Okay. Now, where did I get those numbers?
Coefficient from the equation.
The coefficient from the equation. Okay, so are we clear on that? Because that is the step. If I'm going to show you my not so good writing, that's the one that we connect here. So to connect them, you just need to use the stoichiometric ratio, the balanced chemical equation. So now that we have that, what's the last part that we need to put here?
GB over 1 mole B.
Okay, so this is what? 1 mole of CO2 And that is equals to 44.01. So if you're going to look at the dimensional analysis here, you will see, okay? So somebody asked, where does it came from? Anyone? Where did I get this 44.094 grams? That's the
Is
molar
that
mass
the
of
EF?
C3H8. No, that's the molar mass of C3H8.
How do you find that out?
That's the molar mass of C3H8. Everyone convinced where I get this? I don't want to be a magician, okay? I want to let you know where I got those numbers. So I got this 44.094 when I get the molar mass of C3H8. So that is what? So C3, so 3 times 12, so that's around 36 plus 8. Is that clear?
Yes.
Yes.
Okay. So if you're going to look at this, I cancel this out because they're both grams of C3H8. I cancel this out because they're both moles. And then I cancel this out because they're both moles CO2. And left me with grams CO2, which is the one that I'm looking for. So what will be the answer? So what's the number that come out in your calculator when you do every calculation there?
59.886.
Is it 59? Okay, so 59 point.
I agree with her. It's 59.88 or 59.9.
59.9 or 8?
It's 59.88, but you,
But how many significant figures do I need to put?
oh, two, right. So 59.8.
Yeah, this is the one given. So what's the rule? Whatever the significant figures of the given, that's also the significant figures of your final answer. Analyze. Before we go to the next question of the same problem. Question?
Mm-mm.
So let's try another one. So the same problem, but different question. In the first part, we asked for CO2. Now here, we are asked now for the oxygen. But before we proceed here, so in 1 minute, where's my poll question? Answer this using the reaction that's given there.
Mm-mm-mm-mm.
10 seconds. Okay, Time's up. So why is it only 90% participated? So you just log in and then sleep. Okay. So what's the right answer? Anyone?
3.
3.
So the answer is 3. And unfortunately, only 67% got it right. Okay, so that is what? 2 out of 3. Okay, so if you ask why is it 3? The answer is written there. So for every 1 mole of your propane, you produce 3 moles of carbon dioxide. Okay, so let's proceed with this. So everything is the same as this one. If you're going to look at the previous answer that we have there, the only one that is different is when you arrive, I think, here. So we're going to use the first 2 parts there. So you have what? 20 grams C3H8. And then for every 1 mole of C3H8, you have 44.094. Now, everyone know where I get this? 44.094?
Yes.
So here's the changes that you have, because you're asked for the O2, not the CO2. So the way that you're going to put here, so there's 1 mole of C3H8 and there's 5 moles of oxygen. So convince yourself, why is it that? Where did I get the 5 and the 1? It's here. And then now, for every 1 mole of oxygen, I get 32 grams of oxygen. So just to make sure I'm right, I can cancel out the unit that I can cancel, like grams over grams, moles over moles of propane, and then moles over moles of oxygen, leaving me with grams of oxygen. So what is the answer here?
100.
Is it 100? It's not only 20 times 5. There's a 20 times 5 there times 32 and then divided by 44.094.
72.6.
So 72.6. So question.
Oh, this is the formula to find out the
I would say it's a formula. I would say that's the pathway.
Okay, just a formula. Ooh. I think we use it to find out the grams of whatever.
As I told you, it's the same as the one that I have shown earlier. It's not really, we could say, a formula. It could, the best, I would say, description, that's the pathway, because you came from here, you go to here. So you're going to have how many calculations? 1, 2, 3 calculation. So for you to know, it's just the moles. That's the central concept, to connect with the mass and the number of particles and to connect to the other moles, okay, in a given equation. The other molecular species when you have a reaction. Okay, so I want you to go over this in the recording. Yes, you can use calculator. All you need to do is show the calculator, okay? So let's try to go now with the limiting concept. So in every reaction, whenever you mix reactants, not all of them will react. One of them will be used or will be used up completely, while the other one will remain unreacted, or some amount of the other species will remain unreacted. Now, the one that is entirely consumed when the reaction goes to completion, that is your limiting reactant. Now, the one that remains in excess, we call it the excess reactant. So once one reactant has been completely consumed, the reaction stops because there is no more reactant to react. So any problem that is giving the starting amount for more than one reactant is a limiting reactant problem. So in the previous problem that we have, we assume, okay, that the 20 grams of propane here, that is your limiting reactant. You don't care how many amount of the other species are present, as long as you have that starting material. But there are some instances where you're given different amount of the reactants, and it's up to you to determine which is the limiting and which is the excess, or how much product will be produced. So the limiting reactant concept is the same as this one. So for every, how do you call this? S'mores? For every stuff that you have like this, you're going to need what? 2 cracker squares, 1 marshmallow, and 3 chocolate squares. Okay? So what does it mean for this reaction? You have this one. Now what happened if what you have is 4 of these, 2 of these, and 6 of these? How many of these?
Then you'll have
form?
2 s'mores.
Okay. So if you're going to look at this, you're going to only have 2.
Yes.
Why? Because this one will use up, and this one you will have what? This one will be used up. This one is used up. All of them are limiting reactant. Now, what if you have here, let's say 5, and you have here 6? You still have 6 here. So this is your limiting reactant. How many of these will be left unused?
3 would be left.
Excess reactant here would be 3, and for this would be
2.
what? 2,
2.
because 4 of them will be used up. So that's what the limiting concept is. So the thing that you need to remember, all amount produced and reacted are determined by the limiting reactant. So it is a limiting reactant that will dictate how much will be used up and how much will be produced. Okay? Now the question now is, how are we going to determine which is the limiting reactant? So what you're going to do, whenever you're given the amount, okay, you use each of the given amount to calculate the amount of product that will be produced. The limiting reactant will produce the lesser or least amount of the product. So you don't have to assume that if you use this, how much of the other one you're going to use, or vice versa. So you can always do, okay, I have this amount, this is the amount that will be produced. I have this amount, this is the amount that is produced. So you look at the amount that is produced, the one that is less, that's your limiting reactant. Let's apply that concept here. So if you have this reaction, magnesium reacting with zirconium chloride to produce magnesium chloride and zirconium. So you are asked now here, how many moles of zirconium metal can be produced from the reaction mixture containing 0.5 0.20 moles of zirconium chloride and 0.50 moles of magnesium. So this is just another way of asking which is the limiting reactant. So this is simple. Why is this simple? Because this is already in what?
Moles.
Moles. What makes this more a little bit complicated if it's in grams? You have to convert this to moles, but this is already in moles. So all you need to do, okay, I'm going to use this as the limiting. So how am I going to do this thing? Maybe I can use this one because this is the one that is being asked. Aside from the limiting reactant, which is the limiting reactant, you are asked how much zirconium metal you're going to produce. So what will I put here? So I could say it's moles right away, because that's the ones being asked. So how do I put this here? What will I put on top? What will I put on the bottom?
You put magnesium on the top
Why will I put magnesium?
because it's the MgCl.
It's not given there.
What?
Do you put the
What are you going to put? What do I
CL4 on
put
the
on
bottom?
top? Huh? So CR,
CL4 on the bottom.
okay. And this one?
The ZR.
That's what we're trying to find.
Why will I use magnesium in the first place? Magnesium is out of the picture here.
Because
I'm
I
being
looked at
asked.
the question instead of
No. I'm being asked how many moles of zirconium metal if I use this as the limiting reactant.
did not read the question.
Okay? So, what's the mole ratio that I'm going to put here? 1:1, right?
Yes, CO4.
So that means this is only 0.20 moles of zirconium, because this is cancelled out. Now, how about if it's the other one? How about if it's the 0.5 moles magnesium? So how will this number looks like here? So what is on top? What is on bottom?
Magnesium's on the bottom.
Okay, very good. And the one on top is still
Zirconium.
zirconium. And what will be the numbers that we're going to put here?
1/2.
1/2.
1/2. Now, you may ask, where did I get that, Professor? It's in the equation. For every 1 mole of zirconium, I have 2 moles of magnesium. So in that case, I can cancel the mole of magnesium, giving me with the mole of zirconium. So this is what? 0.50 divided by 2, 0.25. So which is the correct answer here? You have 2 moles of what we call 2 values of moles of zirconium. Now the question now is, which is the correct one? Is it the 0.2 or the 0.25? Anyone?
0.2.
It's the 0.2. Because this is the one that is less, so that means this is your limiting reactant when you're given this amount. Analyze. Now, I want you to go over, I have some recorded PowerPoint slides. So there are some problems that what we call given there. So I would suggest you start studying starting today until you have your exam. I don't want to say that the first exam is the easiest one, because you might be what we call procrastinate and say, oh, anyway, professor said it's easy. Because for me, when I came here in the United States, I don't know the concept of an easy exam anymore. Okay, because for me, when I grew up, the easy exam is I can solve it, whatever is the number that is given, because I understand the concept that I have during the lecture. But here, I'm not sure what's the easy. And usually when I say it's easy, usually my students relax. So we could just say, this is the first challenging exam that you have. Okay?
Excuse me, when is the exam?
Thursday next week, September 24.
Okay.
Professor, I have a question.
Okay?
So in terms of the quizzes, do they get counted towards the assignments?
Yeah. I mean, when we're going to add everything, so if you have a lower exam in the total score, then you can go into what we call replace that thing. But if you're not doing any quizzes, then you're not going to have a high score enough to replace any of the low score in the exam. Let's just say that's my backup plan.
Okay, thank you.
Whenever worse comes to worse. And it's really helpful every semester. Okay? So I always have some backup plan. So when we say backup plan, I have other numbers to look at. Now, the only problem is if you don't have numbers in those quizzes that we have. Because for me, when I do the grading, it's you convincing me that you understand the concept. So maybe exam is not good for you, so I look at the quizzes. But sometimes, what if it's in the quizzes and in the exam, both are failing. So how can you convince me that you understand the concept? So for me, I just try to look at alternatives numbers. But you have to make sure that you have some input on that alternatives number, because if you don't have any input, what's my basis? Okay, so what you're going to lose if you're going to take it? And I can tell you, when I say, what do you have to lose? I'm not sound like Donald Trump, okay? You always say, what do you lose? What are you going to lose? You're going to lose everything. But
Never
for
could
me,
be you. It can never be.
it's not me. I mean, what do they say? Chem is try. So if you take it, you're going to be used to take the exam. If you don't take it, and the first exam is the first time you're going to use a respondus, and every anxiety and problem might be there. But if you have taken already this respondus thing, I think it can ease some of the anxiety that you have. So that's the one that we have it. And the other courses, or the other, there's another section that also using it. Okay? So it's a win-win situation for you. Because as much as possible, I don't want to fail students, but sometimes the students ask for it. What do you see a student ask for it? Well, if you give me something, I'll give you something. If you give me everything, I'll give you everything. But if you give me nothing, what do you expect? I'll give you nothing. It's just as simple as that. Okay? I don't want to stress myself, but let's say you don't do anything. What will I do? Okay? I think it's unfair for other students who did everything, and then they will get a passing score, and in fact they don't do anything at all. So that's the simple rule that I have in life. You help yourself, I'll help you. But if you don't help yourself, why will I help you? Okay?
Do you do a review before the exam?
Usually yes. But the thing is, if you do everything, the quizzes, the poll survey, as I told you, some of the questions are there, and there's a reviewer that is posted already as early as the semester. So if you're able to answer that, I would say you're going to be able to answer the question that we have. Okay? So let's try to proceed this one. So this is a little bit challenging. Why is it a little bit challenging? Because this is in what we call the gram. Where is the reviewer posted? Anyone? It's in the Blackboard.
Yes.
It's posted there, and I mentioned that most of the time. Okay, so let's solve this one. We have ammonia, 2 moles of ammonia reacting with 1 mole of carbon dioxide to produce urea and water. So what happened if we decide to react 10 grams of this?
Yes, I am.
Okay, so how many grams of urea do we have? And then in addition to that, how many grams of the excess reactants are left at the end of the reaction? So you're going to do 2 calculations here, wherein in those 2 calculations, you're going to utilize both 10 grams of this starting material. So first 10 grams of this, determine how much grams of urea. And then in the next calculation, 10 grams of this, and then how many grams of the urea. So I'm going to use the next page here. So 10 grams ammonia. So what's the next thing that I'm going to put here? So I can put here 10 grams CO2. So 1 mole of CO2, 1 mole of ammonia. So what is 1 mole of ammonia equal to? NH3, so that's what? 14 plus 3, so 17.024 grams. And this one, from the previous slides, we have 44.01 gram. And then what's the next thing that we're going to do? So we need to go back to this one. Okay? So 1 over 1 for carbon dioxide and 1 over 2 for NH3. CH4 and 2O. No, this is 2. So where do I get the 1 over 2 and 1 over 1? If you're going to look here, okay, that's where you get that information. And then once you get that, the next thing that you have here now is for every 1 mole of urea, you need to get its corresponding molar mass, which 60.06. So where did I get the 60.06? Anyone?
Molar mass.
Finding the molar
The
mass
molar
of each
mass.
of the.
Urea. Okay? So I can cancel out these grams, the moles, and the moles here, giving me the grams of the urea. The same thing here, giving me the grams of urea. So what are the numbers of the urea that I have? For the ammonia, 10 grams ammonia, how many grams urea do you have?
17.6.
17.6.
17.6. Now, if you have 10 grams of carbon dioxide, you will have
13.6.
13.6. Now, based on the question that we have here, we can now answer this question. So what is the answer to this question?
16.6.
Is it the 16 or the 17?
17.
So which one is the correct answer for this question?
17.
17, because that's the
It's
maximum.
13.61
This one.
because it's
Because
lower.
that's the one that's less.
Yeah, it's the less reactant.
So your limiting reactant is the
Thank you.
CO2.
Carbon dioxide.
Okay. So what does it mean? Of the 10 grams, all of the 10 grams of CO2 will react. Okay. That's the interpretation there. Because the next question that we have here, how many grams of the excess reactants are left at the end of the reaction? So what does it mean here? Not all the 10 grams reacted. So the next calculation that we have, the same thing as we have here, but at this time, we need to determine the amount of the ammonia that react. So you have 44.1 grams of CO2, 1 mole CO2 times. So what is the mole ratio of these two? For every 1 mole of CO2, you have 2 moles of ammonia. So I can put here 2 moles of NH3 for every 1 mole of CO2. And then for every 1 mole of ammonia, I have 17.024 grams ammonia. So try to do the calculation, because the answer there will give us the amount of the ammonia. So how much did you get?
7.73.
7.736.
6, yeah.
So what does it tell us? When you reacted 10 grams of carbon dioxide with 10 grams of ammonia, only 7.73 grams of ammonia will react. So to answer the question that we have, so it's 10 minus 7.73 to get us the amount of ammonia that remains unreacted.
Will a problem ever ask for the percentage of these? Like,
don't be excited. We'll be on that later on.
Okay. Okay, sorry.
2.27.
Okay, so you have 2.27, or we could say around 2.3 grams of ammonia remains unreacted. Okay, so if you're going to look at this now, when we determine the 10 grams each of the reactant, okay, one of them producing 17.6 and the other one 13.6. So based on the one that has the less amount, that's the one that's limiting reactant. And if that's the limiting reactant, that means the whole 10 grams of that material will be used up. Now, the next question being asked is how many grams of the ammonia reacted with 10 grams of CO2. So to do that, we did the calculation wherein if we use 10 grams, how much or how many grams of ammonia will react with it. And based on this, we need 7.73 grams. And it makes sense because the ammonia that we have here, this is the excess. So that means the amount that it has is over 7.73. And since the question is asked how much was unreacted, we just subtract the given 10 grams with the 7.73 that we calculated. Okay, that's going to react with CO2. So we have there 2.3 grams that remain unreacted. Okay? So the last part that we have in this chapter is still using this question is the yield. Now, this is the only time we discuss it, but when you go to organic chemistry, you're going to determine the yield that you have in some of the reaction. So when we're talking about theoretical yield, that's the maximum amount of product that can be obtained by a reaction from the given amounts of the reactant. And usually theoretical yield, we could say, that's also the calculated yield. Compare it with the actual yield, the amount of product that is actually obtained. It could be a measured amount, or it can also be called as the experimental yield. Now, in the percentage yield, it's just equal to actual yield over theoretical yield times 100. So in the given problem that we have, okay, so we say when we reacted 10 grams of ammonia and 10 grams of CO2, the theoretical yield is 13.6 grams. Now when the reaction was carried out, 9.3 grams of the urea was obtained. So what is the percent yield here?
Percent. He's like, nah, I got excited.
Okay. So if you're going to look at the percent yield here, it just equals to what? 9.3 grams over 13.6 grams times 100. And what do you have?
71%.
Is it 71? Everybody get 71?
No, I got 68.4.
So it's 68%. Now you may ask, why did I just put 68, not 68 point something? Because I have here two significant figures. I just can express it into significant figures. So question.
We do the homework. Do you think that's also good practice?
Oh, I just, somebody has, have to, somebody is, have to unmute that. Okay. So what's the question again?
So are the questions on chapter 3 like homework on Cengage similar to the
Yeah.
Okay.
I mean, it's not that it's going to be the same question, but the concept that you have there should be the same.
For chapter 2, we had to learn about like hydrate. So
no, not necessarily. I'm not sure if they include it in the OWL.
they did include it in the OWL.
It did include in the OWL. Then it's just like you're just going to add the word hydrate. The prefix is the number of water that you have in a given formula.
Okay, thank you.
So question before I go to the quote of the day, and I think some of you has an idea what it is.
I actually have a question about the exam. Are you allowed to tell us how many questions will be on it?
As long as it's over 100. So it would be around 25. I might give you the number by next meeting.
Okay, thank you.
So maybe you're familiar with the quote of the day. Oops. So I'm telling you, okay, the things that I asked you to do, that's the way for you to survive the course. So, question, we still have what? More than 5 minutes. If you have any question. So, by this time, you should be what we call starting to do the review. Okay? So, the idea that I have is after we finish the chapter, you're going to work on the blackboard and the chapter quiz, not wait near the deadline to do it. Maybe I'm a little bit what we call annoying telling you this one, but don't worry. After the first exam, if what I say is right, I'm not going to annoy you. But if what I say is wrong, I'm going to annoy you more. Okay? So this is for your own good.
So we have until 5 to complete chapter 2 quiz.
Yep.
Okay.
Yep. So it's a 10 minutes thing minus the setup for the respondus. And for chapter 3, it's you have a calculation there. So I'm giving 20 minutes. And I think I have, if I'm not mistaken, less than 10 questions because 2 or 3 are calculation questions. So the same way that you are asked to do in that calculation, that will be the type of the exam questions that you will have. That's why after chapter 3, I still have a dry run that I'm going to post and for you to do during the weekend. So I would say I'm going to cover everything that you need to do. And if you do it, I would say you will survive the chem. But if you're going to do it at the last minute, please don't blame me. Okay?
Okay.
Because I told you from the Mandalorian, this is the way. So question, any more question? We still have 3 minutes more.
Office hours, do you still have them this week?
We went last Monday. 2 of you saw me last Monday. So that's the only time that I'm available, unfortunately. So I expect the Monday next week will be full packed because there's an exam. You can also avail, I emailed you, I think weeks ago, about the tutor, but I think they only have particular days that they are available. Okay? I don't have any question from chapter 2. Unlike chapter 1, most of you email me about a particular number. Because what I have, if there's a question about chapter 2 or chapter 3, I'm going to prepare a video about, recorded lecture, a video about it, how to answer it, and then post it. But no one emailed me. So one who emailed me, I was able to answer it yesterday.
So far in the OWL for chapter 2, it's pretty easy. It's just, where was I? I was somewhere. I'll probably email you later just because I couldn't remember.
Don't email me at the last minute, okay?
When's the OWL due? The OWL's due today?
Thursday.
No, but I'll probably email. This isn't about the chapter. This isn't about the quiz. I can finish that. I'm talking about the OWL because I'm on the 5th one. And it's just there's a problem I was having, and if I can't figure it out in my notes, I'll just email you today.
Yep.
Okay. That was it. I just wanted to know if we could still email you about the OWL.
Of course, yeah.
Okay.
I usually answer. If ever I don't answer, so that means I don't have any answer for you. Like if you get a problem, it's already the deadline. I can do anything for that.
Oh, no, it's not.
So, I mean, it's not for you. It's for the other students. So sometimes if you email and you don't get an email back, so try to think, why did he email? So I said, what will I email for? I email, it's useless already. Because some of you said that you get the problem during the OWL and it's already the deadline. So what can I do? Even if I answer, I cannot give you anything.
It's too late, yeah.
Yeah.
Okay, thank you though. That was it, honestly.
So any more? So I would say
Mr.
start
Majika.
studying. Okay, yep.
Ms. Majika, because I still get a little bit confused with it. For the chapter 2 quiz that's today, we go to respondents Blackboard and it's underneath the assessments, right?
Yeah.
Okay.
The one that is due today is in Blackboard. The one that is due on Thursday is on OWL. And then by 5 p.m., you're going to have the chapter 3 already, quiz in Blackboard.
By today, 5 p.m.?
Yeah, because I just don't want both of them to be up because someone messed up answering it. So I said, okay, I'll finish the other one first before I posted the other one.
Okay.
But on Thursday, there might be another one that will be up. Okay, so before you answer your quiz, make sure you're on the right quiz because I don't want to get an email because sometimes, do I need to answer this thing? Okay?
Okie dokie.
So if not, stay safe. See you on Thursday.
See you Thursday. Thank you again.
Bye-bye.
Bye, Mr. Majika.
Bye.
Thank you, Professor.
Bye.
Thank you. Have a good one.